Okay, in this video, we're going to do a quick overview of the classification of stars. So, stars were classified first by Hipparchus. Hipparchus had a scale that went from 1 to 6. It's called the Hipparchus scale. He said that 1-class stars, when he observed from Earth, were the brightest stars in the sky, right? And he said class 6 stars were then the dimmest that he could see with his eye in the sky. So the difference between his class 1 stars and his class 6 stars was that he said that a class 1 star was 100 times brighter than the class 6 star. So that's when we had a catalog of scales then. So we said, if you look at the numbers, there's 2, 3, 4, 5. There's 1, 2, 3, 4, 5 different loops. If you take the fifth root of 100, you get the number 2.5. So what he said was, for every difference in magnitude, so every change in magnitude, all you have to do is take the number 2.5 and raise the power of that change of magnitude. You can compare the brightness of the stars. So let's say I want to compare the brightness of a class 1 and a class 3 stars. That change in magnitude there is 2. So if I do 2.5 squared, that tells me how much more brighter a class 1 star is than the class 3 star. However, as our recent advances with telescopes go a lot better, clearly we can see much brighter things in the sky than we can see with our naked eye. So that had to make that more bright things now, they have negative numbers. So that's when we came into our new apparent magnitude scale. So what apparent magnitude is, it's how bright the star appears from the surface of the Earth. Okay, so how bright a star appears on the surface of the Earth. But the problem then with that was, if we're on the Earth and we're looking at all these stars, we don't know if they're super bright because they're more luminous, they're bigger stars, or if it's because their distance is further away. So that then there's the absolute magnitude. So what the absolute magnitude is it's equal to the apparent magnitude if all of stars were at 10 parsecs away. So what we're saying is we basically made all the stars be the same distance, 10 parsecs away from the Earth, and we then compared how bright they all were to each other. So what is a parsec? So a parsec is the distance to an object that subtends an angle of 1 arcsecond to the Earth. So there's that angle there of 1 arcsecond. You don't even have to describe it. You can just draw a picture of the Earth's orbit. So there's the Earth, and we know the Earth is orbiting around the Sun. Diagram, clearly not scale. So what happens is we know when we look at stars, we're going to say that they're really distant stars, really further away stars. We say they're basically fixed in place. So when we observe an object that's close, we see how does that star change its location compared to those background stars as we orbit the sun. So as we orbit the sun and we look at that same star, maybe 6 months later, we can see how that star shifted compared to those background stars. And that's then how we measure its distance. So again, 1 parsec is the distance an object is away, when the angle it subtends is 1 arcsec to the Earth's orbit, or that base there we can say is 1 AU, 1 astronomical unit. So then, how we related those equations then, or the apparent magnitude and the absolute magnitude, is we said that the apparent magnitude minus the absolute magnitude is equal to 5 log to the base 10, so use your log button, everywhere else in physics you use the natural log button, of the distance in parsecs divided by 10. Now this equation is really important and it'll only work if this distance here is in parsecs. They like to give you the distance in light years, and you need to remember how to convert from a light year into a parsec. That equation will give you in your data sheet. So again, if they give it to you in light years, a light year is since light travels in 1 year, you just convert from your light years into your parsecs, and then that's the number you pop into this equation. So what the little m stands for, the little m is our apparent magnitude, and the capital N then is going to be our absolute magnitude. So it allows us to compare the brightness of stars. Then what we did is that we had other laws that we're going to look at in later videos. We can classify the stars now into different temperatures as well. So OB, a fine girl, kiss me. We're going to look at how we actually find out the temperatures in later videos. But just because we're looking at this video, the classification of stars, these are how we classified our stars into these spectral classifications. And you learn the temperatures. So the temperature of an O-class star is around 50,000. So you just lose these numbers, you'll never be wrong. B is half that, 25,000. An M star, you just divide it by 10 to get 2,500. A class G star is our sun. So a G5 star is the one that is our sun. So G5 star, our sun is around 6,000. Okay, so that's one you want to remember. The other ones you can always just pop in based on these numbers, and an A is 10,000 because 10 is just easy to remember. Okay. Our sun is basically a yellow-white color. Okay, so any stars that are cooler than our sun are going to be like a reddy color, reddy orange color. Any stars that are brighter than our sun become those blue colors because the blue is the hotter colors. And we're going to look at a later video again about how we can relate the wavelength of light we see from these stars to determine what their temperature is. So again, when we observe the stars, we get certain wavelengths hitting us on our telescopes over here on Earth, and then we use a law called Wien's law in a later video to figure out what the temperature is. Okay, the other thing we can look at is that we can look at what the lines are in the spectral lines. So if we see hydrogen-Balmer lines, we know that it's always going to be an A-class star. If we see metal lines, we know it's a cooler star. If we see ionized metal lines, we know it is getting slightly hotter. And then you've got your hydrogen-Balmer lines. So what are hydrogen-Balmer lines? We know that all atoms exist, all electrons exist in the ground state, n equals 1. N equals 2 is then our excited state, n equals 3 is the next excited state, and so on. In A-class stars, because they're so hot, the electrons aren't in the ground state, they're in the n equals 2 state, right? So because it's slightly hotter, they're slightly excited. And then those electrons get promoted to higher energy levels and they fall back down, emitting wavelengths of light. So that's what we can see. We see these, observe these hydrogen-Balmer lines. So we call the hydrogen-Balmer lines because the electrons are in the n equals 2 state. So if we observe these hydrogen-Balmer lines, we know it's from somewhere hot, and we know it's from roughly around a 10,000 degree temperature star. So we know that's going to be an A-class star. And again, the way to remember it is, oh, be a fine girl, kiss me.